Look, I don't want to make this harder than it is, but you guys should be capable of something on this order. So allow me to just say things out loud that I think you should already know. If I want to draw a free body diagram, I begin by representing my object as a point. Can anybody tell me a force that is acting on my object? Is that the only force that acts on my object? Are those the only forces that act on my object? Okay. Then I need probably go with some kind of coordinate system that I could use to break this problem up. I have to align it somehow. Can we come to an agreement that this is unbalanced? And since this thing is traveling in a circular path, I'm going to analyze it in such a way that I align this with the direction of the acceleration, which should be towards the center. And then I will have the y direction, like so. My next step would be to take any off-axis forces and break them up into components. So I'll have a portion of the tension upwards and a portion of the tension sideways. Nothing odd here, correct? Stuff we've done before. Can I set the net force in one direction equal to 0 and the other one equal to ma? All right. So T sine theta equals ma. T cosine theta equals mg. There's nothing new here, right? Nothing new. This object's traveling in a circle, though. It's not changing its speed, it's changing the direction of its motion. So I will probably rewrite this as T sine theta equals m v squared over r. T can't be in my answer, neither can r. Can anybody think of a way to get rid of r? Sorry? That'd be a way. L and theta can be in my answer. T can't be in my answer. Is there any way to get rid of T? So M's cancel. Well, that gets you V. That's not what I asked for. I asked for the period of oscillation. I asked for how long does it take for it to go in a circle. I suggested to do that you think of distance equals rate times time. I want time. You have rate. What is the distance? Circumference. Solve that for T, please. And if you have more than one trig function in your answer, you're wrong. Because I know some of you think you're very smart, but you should reduce down your trig to the least number of trig functions necessary. So, a lot of you guys are struggling here. There's not a lot of struggle, I don't think, that is necessary. V is the square root of GL sine theta tan theta. Not a whole lot I can do about that, but I have 2 pi L sine theta equals the root of GL sine theta tan theta times T. I just want T. I want the period of oscillation. So when I divide these, I get kind of a mess. I'm going to pull a 2 pi out front. I'm going to have L sine theta in the numerator and the square root of all of this garbage in the denominator. You can clean that up, and you should. If I square the numerator, I can put it under the radical. As L squared sine squared theta divided by GL sine squared theta over cosine theta. All right, isn't that what sine theta, tan theta would equal? You guys see why I wrote it this way? So I can cancel out the sine squareds. Do you guys see that okay? Looks like I can also cancel out an L. All right. You should remember from just last day that a pendulum has an oscillation that is equal to square root of L over G. 2 pi shows up for anything that has oscillatory qualities. That is because of the relationship between oscillators and circular motion. And it should be coming clear to you that there is a clear connection between things in circular motion and things in oscillatory motion, at least mathematically. These two things aren't the same. But remember, to get here, we had to say that theta equaled sine theta for small angles. Sound familiar? Put those calculators in degrees. I don't want to screw this up. More importantly, I don't want you to. Tell you what. Let's go. Let's cosine of 1 degree. Point what? 9. How many 9s? Then a what? Oh, almost a 9. Let's cosine of 2 degrees. Cosine of 3 degrees. 8, 6. Cosine of 5 degrees. 9 what?
6.
Wow. Do you see it? I'd say that cosine theta equals 1 for small angles. Does it actually equal 1? No. Is it pretty close to 1? Well, heck, you guys won't even write that many decimal places as it is. So yeah, I'd say it's 1. I'd say this is 1. Small angles. So if you hit the tether ball really hard and it goes around really high with a big angle, not so much. Small angle, definitely. It's as in the same range as that is based on the same assumptions we made. Now, I didn't want to do this for this particular problem. I did want to show that this was true, to show the connection between circular motion and simple harmonic motion. I want to do this because we have things that are going to be traveling in circles today. And I wanted to use a problem that we had already done. But it seemed like it was much harder to get to the solution than I anticipated it would be. But today we're talking uniform gravitational motion, or Newton's law of universal gravitation. Newton had his hand in everything. I don't think people fully appreciate the fact that when Newton wrote a book about physics, he wrote about as many aspects of physics that he was studying, and that was all of them. So although no electronics were in his original book, all sorts of optics, sound, vibrations, everything else, he really was trying to create a full theory that would cover anything that moved or had motion associated with it. And that included, in his estimation, optics, which is why there's something called Newton's rings, which is the optical diffraction pattern you get under certain conditions. But when it comes to Newton's law of universal gravitation, I think there's a lot of apocryphal stories about him sitting under the apple trees and his understanding of how he believed gravity operated. It's more than just an understanding. It really is very predictive. It gets us to the moon. It is the Voyager spacecraft and how they got out to where they are. Newton's law of universal gravitation is simplistic, but understandably, it is only used in certain circumstances, and you'll see why in just a few minutes. First, it's universal, so we believe this particular law is the same everywhere in the universe. That's important, because so far we've been calculating gravity by saying mg. But mg is very fixated on the Earth. G is the acceleration of gravity near the surface of the Earth, which makes this incredibly useless if I want to go anywhere but the Earth, or if I want to start getting further away from the Earth. So Newton's law of universal gravitation is a formula for calculating the force of gravity between any two objects. And it is, I'd say, elegant in that it's pretty simple. But it belies a certain complexity that's not there in the formula. First, I'm leaving out all the information about direction because I wrote it in third period, but it was just too much for the introduction. So this is just the size of the gravitational force. And in the formula, it should be clear to you that there are some things in the formula that are being announced to you. First, it deals with two objects, any two objects, mass 1 and mass 2. It requires that you know how far apart they are. R is not the radius here. R is the separation distance. Be careful. We're going to be dealing with orbits, and orbits will have a radius, but the radius and the separation distance do not have to be the same. So in the gravitational function, R is the separation distance between the center of mass of one object and the center of mass of the other. G is what's known as the universal gravitational constant. This makes our units work out. Because if you look, we're taking masses and multiplying them together, that's kilograms squared, divided by the distance squared, that's meters squared, but we have to be left in something called newtons. Now, of course, this value would be different if we're dealing with feet and slugs or feet and stones, but we are dealing with kilograms, meters, and seconds. So the unit for G is 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. It's an incredibly small number. And that's not something I say lightly, considering how overwhelmingly large gravity is around us. But remember, at the beginning of the year, I made it very clear that gravity is the weakest of all the forces, but has one of the longest ranges of all the forces. This value for G should tell you that it takes an incredible amount of mass being relatively close together in order for you to get any measurably large value for the force of gravity. All of us are experiencing forces from every mass around us. So between you and the chair, you and the table, you and the cafeteria, you and people in the other building, you're experiencing forces from all of them. But remember, they're scaled by this value. And your mass is small. Those forces are unmeasurable because they're so small. Times 10 to the negative 11th, incredibly small. In order to really experience a force of gravity, you need something very big, overwhelmingly big, to overcome the fact that this distance, or this expression, is very small. Also, notice that this is an inverse square law, which means that the amount of force that you actually experience drops down radically as you increase the separation distance. Does that make sense? We're going to experiment with that first. This is an inverse square law. And what I mean by that is I want you to do some experiments with what inverse square law problems look like. I hate these kinds of problems, but they are super common on the exam. And I don't know why professors feel like these are the kinds of problems that you need to know. But let's do one or two of them so you can kind of get an idea of what I'm expecting or what is going to be expected in some circumstances. I have two objects, mass 1, mass 2, separated by a distance of r. They currently experience a mutual force of attraction of 20 newtons. By what factor do I have to change R for them to experience a force of 10 newtons? By what factor do I have to change R for them to experience a force of 10 newtons? What is being changed here? Which variables change? R changes, and in response, the force changes, correct? So everything else stays the same, right? Consider constructing an initial relationship, M1, M2, G over R initial squared. We know that equals 20, right? But we also know M1, M2, G over R final squared is going to equal 10. Do you see what I've constructed? Two relationships, and those two relationships are clearly related by those variables. So, if I want to find out how the final distance is related to the initial distance, I could just divide these two and turn it into a ratio. If I do, I'll get M1, M2, G over Ri squared divided by M1, M2, G over R final squared equals 20 divided by 10, or 2. Can you solve this for R final? This is a method for doing this. There are other methods. They're all relatively the same. This is just the method I'm doing this here. So anything that doesn't change just cancels out. And in this case, I'll be left with R final squared over R initial squared equals 2. So R final equals the root of 2 times R initial. By what factor? I have to change it by the root of 2. Here, you do one. You guys ready to do yours? I have two objects, M1 and M2, currently separated by a distance of 10 meters. I would like to reduce the force by a factor of 4. How far apart should they be placed? I'll say again. I have two objects, M1, M2, separated by 10 meters. I would like to reduce the force by a factor of 4. How far apart should they be placed? Give it a try. Okay. Again, find the force of gravity on you using Newton's law of universal gravitation, using the mass of the Earth, the separation distance being the radius of the Earth, and G. And don't forget, if you want a quick estimate of your mass, just take your weight in pounds and divide by 2.2. I'm doing this exercise because people can't use their calculator correctly. As we've seen several times walking around, you make silly mistakes, or you forget to square the denominator, or you forget to put the notation in correctly. You got to nail this stuff, because if they're going to give a problem like this on the exam, they're likely to use numbers. They almost always do. So I would encourage you, multiply across on the top, write it down, multiply at the bottom, write it down, and then divide separate. You're not saving yourself any time if you get the answers wrong. But you want to know if you got it right or not? This still has to equal mg. It still has to be weight. This still has to work. If you divide by your mass, you should get g. That's how you'll know if you did it right. So take this number, whatever it is, and divide by your mass, what you used for your mass, and you better get 9.8. If you don't, you blew it. That's how you know if you did it right. Also, since you're keeping notes, and now we've learned something, right? If you want to figure out the acceleration of gravity on another foreign planet or foreign body, you can do this, where this is the mass of you. Cancel those out, and you get mass of planet, g over radius of planet squared would be the acceleration of gravity on a different planet. So if you want Mars, you need the mass of Mars and the radius of Mars. You want moon, mass of the moon, radius of the moon. Wouldn't make any sense to even say the word Jupiter, Saturn. They don't have a surface. But these do. So this is how you can calculate the acceleration of gravity. What I really want to get to, and clearly that's not going to happen, is I want to talk about orbits. Newton's law of universal gravitation has significant limits. One of the limits is that it only is useful in the two-body problem. Has anybody heard of the three-body problem before? Not the current book or television show that's on Netflix, but the actual idea of the three-body problem. The three-body problem is a contingent. It's generally associated with the electrons around the atom, but it's any system in which there's a force that can only be calculated for two objects at a time and wants to know what happens when you introduce a third. It's an odd perturbation, and it's true here. Our problems can only be two-body problems. For any of the things we're going to do, it's going to be the association of gravity between two objects at a time. But the truth is, if there are three objects, then you'll have to calculate the force of gravity multiple times to get the force on each of the objects. And yeah, there's going to be some homework questions about that. They're largely one-dimensional problems, three objects in a row kind of thing. But I want you to also understand the implications of Newton's law of universal gravitation. The force on these two objects is equal and opposite. If the object in the center is large enough, then it can stay relatively stationary as the other object uses this force as a centripetal acceleration, or uses this force to provide a centripetal acceleration. The basis for all orbits is that the gravitational force is causing the object to travel in a circular path. We'll discuss two kinds of orbits: circular orbits and elliptical orbits. Circular orbits obey this rule, where the unbalanced force is equal to MAC. The moon around the Earth is very close to a circular orbit. In fact, that's what I want you to do tonight. I want you to tell me how long it will take for the moon to go around the Earth using what we did today. The answer is 28 days. It's not rocket science. Prove it. I'm going to give you what you need in the next, 45 seconds. First, mass of the moon, mass of the Earth, g, over the separation distance between the Earth and moon squared. That's the force. What's the thing that's doing the orbiting, and what's the thing that's relatively stationary? Earth is stationary, moon orbiting. So on this side, the mass here is what's orbiting. Put that in your notes. This mass is the thing that is doing the orbiting. It's what you think is moving. For this problem, that's the mass of the moon times AC. Now, I'm going to write two other hints down. AC is going to be v squared over r. In this case, r is also the separation distance. And what we did earlier, 2 pi r equals v times t. You will need these things to calculate the period of the orbit, but this will be in seconds. You can pack up, but I'm going to give you a few helpful hints. Bye, have a good day. I don't think you'll need anything else, but that's what I think you'll probably want to walk away with. There are some things about this that I think will help you if you're careful. For example, I want to keep reiterating that this R is the separation distance. And this r and this r are the radius of curvature. Today, I'm going to probably take issue with those. So I want to continue to emphasize the difference between those two. We said in this problem that I wanted you to find the period of the moon as it goes around the Earth, assuming it orbits the center of the Earth. So that's why these are all the same value today, right now. It's not going to stay that way. So I want to say to you that we have to combine all of these things so that you have solved for t. I wanted the period. And that answer would be in seconds. Let's do this in 2 steps. Let's do this step first and take a pause after we do. That's going to be mass of moon, mass of Earth, g over. From this point forward, I'm not going to write EM, Earth-Moon distance. I'm just going to write capital R. And that's going to equal mass of moon v squared over r. The reason why I want to stop here and take a minute is if we solve this for v, we cancel out the mass of the moon. That's not arbitrary. I think it's interesting to note that what we are left with is an expression for the velocity of any orbit. And the velocity of any orbit does not depend on the thing that you put in orbit, right? The mass canceled out. The only thing that determines how fast the orbit is will be the separation distance and the size of the gravity well. ME is the thing at the center. It's the gravity well. So if this was the Earth around the sun, a satellite around the Earth, a moon around Jupiter, the thing at the center is the mass that's here. So it tells you that no matter what you put into orbit, or no matter what orbit it's at, everything at the same altitude has the same velocity. Put in the radius of the Earth here and the mass of the Earth. You'll find out how fast you have to launch rockets to get them into low Earth orbit. Things in low Earth orbit are just outside the radius of the Earth. They're just outside the atmosphere. And when you look at the size of the Earth and how thick the atmosphere is, it's not much but a couple of tenths on the decimals of the radius of the Earth. By the way, the radius of the Earth, 6.37 times 10 to the 6 meters. So take a minute right now before we go any further and just tell me how fast do you have to launch a rocket in order for it to be in a low Earth circular orbit. You already have the mass of the Earth from yesterday, 5.96 times 10 to the 24th kilograms. If we want to find the period, the truth is we need to make another substitution, right? That would help us find the period. So I could just solve this for v and sub it in. So it's a little inefficient, but let's do that now that we've played around with the velocity a little bit. So I'll get 2 pi r over t equals the root of MEG over r. Now, there is something I want to see here. I want you to see something specific, but we'll do this in steps. First, I want to just get t by itself. So I think we can do that pretty easily, right? Cross multiply would do it. So I'll get t equals 2 pi r times the square root of r over MEG. That's the result of me cross multiplying. I just flipped the fraction when I cross multiplied. Is that okay? I'm going to collect the r's. That okay? So, are you in any way surprised to see that when we found the period of oscillation of an object in orbit, it was 2 pi times the square root of some stuff? Didn't everything that had a period in oscillatory motion have 2 pi times the root of some stuff? That's not accidental. That's another reinforcement that circular motion and oscillatory motion are the same kind of motion. But look carefully here. If you're really paying attention and you really want to understand this stuff, notice that this could be written as You might not see it, but remember when I said that it's always inertia over restoring force? And for a pendulum, that inertia was just L over G because the L represented the portion of the inertia related to the moment of inertia of a point mass. This is still representing the moment of inertia of a point mass in the numerator. And this is the restoring force, the portion of the force of gravity causing the planet to be in circular motion. It's the same stuff, it's just laid out again right in front of you. So since I did all the algebra, the heavy lifting, how long does it take the Earth to go around the sun? We're doing these because you need to practice the big numbers. So if I want you to tell me how long it takes the Earth to go around the sun, what information from me will you need to make that happen? The mass of the sun is 1.99 times 10 to the 30th kilograms. It's a big boy. Relatively small on the compared to other stars. Will not go supernova. Yep. You will need the Earth-Sun distance, which is 149.6 times 10 to the 9th meters. She'd be a long way out there. But although these are the parameters for simple circular orbits, I want to take this and go backwards a little bit for just a minute. So let me just take a look. We have our t equals 2 pi times the square root of r cubed over, I'll just leave m as m, nothing special, m times g. It represents whatever our gravity well is. Square both sides. And multiply by mg. And then prepare for a short story. I always stay late. Where am I going? This is one of Kepler's laws. What's amazing is twofold. First, we showed this for circular orbits. He showed it by interpreting the data that he got from observations from the Earth, which is one of the moving planets. It's amazing to me the kind of work he must have done in order to put this relationship together. But more than that, he showed that it worked even for all orbits. You see, we did this for a special subset of orbits. What? Circular. Most orbits aren't circular. That was one of Kepler's other laws, that the planets actually all orbit in elliptical orbits with the gravity well located at one of the foci. You're supposed to know things about ellipses, and my understanding is that you do. Like that an ellipse has 2 foci. You know that, right? You know that a circle is a subset of ellipse, right? Just like a square is a subset of rectangle. A circle is an ellipse where the foci overlap. It's also an ellipse where the semi-minor axis and the semi-major axis have a ratio of 1. This is minor and major. Eccentricity is the ratio of minor to major. A circle has an eccentricity of 1. Most orbits are almost all slightly elliptic. The Earth-Moon orbit is actually very circular. In fact, Earth's orbit around the sun is pretty circular. Some people seem to think that the reason why we have winter and summer is because we're closer to the sun sometimes and further away others. That is not true. It is because of 23.6 degree inclination. That's what causes it. It's about how much solar radiation you get per flux against the surface of the Earth. Solar flux determines it. But I want to point out something about orbits that you do need to know. Most orbits are elliptical, and because they are elliptical, we need to talk a little bit about the differences between an elliptical orbit and a circular orbit. So I'm trying to get this this thing out of here, but I'm having terrible trouble doing so, but I'll do my best. There we go. Get that guy out of there. All right, here we go. So let's put the sun at one of the foci, and let's say we have a planet that is orbiting, and let's talk about a couple of places during that orbit. Let's talk about those places. It should not be a big surprise to you that in an elliptical orbit, the force of gravity on the object is changing all the time. Can you see why that has to be true? It's not that the masses are changing or G is changing. What value is changing all the time? R is changing. So when we are at closest approach, perigee, we have the strongest amount of force. And we are at farthest away, apogee, we have the smallest amount of force. It's at those 2 points that the force is perpendicular to the tangential velocity. Because remember, all velocities on a curve are tangent to the curve. So when we are furthest away, our velocity is tangent, and when we are closest to, our velocity is tangent, but only at those 2 points is there a right angle between the force and the velocity. When we are, say, at position number 1, do you notice that there is an angle now between the velocity of the planet and the force on the planet? And that angle is clearly contributing to 2 things about the planet's motion. The force is changing the direction of the planet and slowing the planet down. Is that clear? Let's look at that angle. That has to be true. That force is getting smaller as we get further away. You can see why I probably don't talk about how do we deal with the period when this force is never constant and the acceleration is never constant. But at this moment right here, again, the velocity is tangent. Force is clearly slowing it down. There is an instant here where that force is not slowing it down. And for that instant, there's a bit of a relationship between the force and the velocity that we could discuss. But this velocity is too slow for it to be in circular motion, which is why it's falling underneath the circle, meaning the circle, based on the radius where we are, looks like that. We're going too slow to go in that circle, so we fall below that circle when we are here. You understand what I'm saying by that? That's why we're not in a circular orbit. So we make it to, say, here. And now, again, our velocity is still tangent to our path. Now we have a contribution to the force in the direction of motion, and our planet is speeding up. So we are fastest here, slowest here. All good so far? A basic elliptical orbit. Now, when we make it to here, we're actually traveling too fast to be in circular orbit. A circle drawn at that point would look like that. We're going too fast to be in a circular orbit, so we travel outside of that orbit. So when we're out at the furthest point away, we're too slow to be in a circular orbit there. And when we're so close, we're traveling too fast to be in a circular orbit there. Of course, if you're trying to change orbits, this is how you do it. You suddenly increase your speed when you're at lower orbit. That puts you in an elliptical orbit. You wait till you get to the farthest place away, and you increase your speed again to be in a new circular orbit. That's how you change orbits out in space, is by manipulating your speed at precision moments. This moment and this moment. I have 1 minute left, and it's not enough to do anything meaningful except this. We made a massive mistake. Massive. And it's not that massive, but it is a mistake. It's not 27.44 days. It's not. Because the moon doesn't orbit the center of the Earth. This is the Earth-Moon separation distance. But remember when I said 2 units ago that if you take an object and just chuck it through the air, it will rotate about its own center of mass? This system rotates about its center of mass. the center of mass of this system is located just below the surface of the Earth. So the actual orbital radius is from the center of mass to the object that's orbiting. We will have to make an adjustment to our work to account for that.